recorder. All right. One of the things that occurred to me, I went back and looked through the recording last week and noticed there were two or three things that we had not talked about that seemed to me that might be good precursors in terms of what we really need to talk about as we get into these articles. And so I wanted to kind of touch base with a few of those precursors, and I put those things up on the As You Learn site. We're going to kind of walk through those, and I know they came up kind of late. I actually had them up there and then forgot to turn them on, which was one of those things too. But now they're all on, and plus we'll do a little formative assessment for you to work on between now, this week, and next week. And I want to get out of the way this idea of general understanding of descriptive statistics, plus kind of the understanding of some of the basic tests used to identify significant differences between means. And so in the interest of kind of getting those out of the way and moving on, that's kind of what we'll, or not kind of, I don't know why I say that. That's what we'll talk about this afternoon, and I'll try to walk through, examples and all. And I've put up a formative assessment document for next week to be done by next week. You don't submit it because what I'll do is, you kind of give it to you and give you the data files to work with, and then before class next week, or perhaps during class next week, we will kind of go through it, record that, and also make, allow you to kind of self-check, and at the same time make some, ask any questions you need to ask about those particular things. So I thought we would handle it that way, as opposed to having you submit something and then deal with it in class. That's normally what I do with the stats classes I teach, is that we do up until the final sort of exam piece. And we won't necessarily have a final exam piece in here. We'll just be doing the stats thing parallel with the design pieces that we'll get into here beginning next week. So we will use some of the stuff from that article that I gave you, particularly having to do with the analysis and the questions and that sort of stuff, next week as we kind of work through this formative piece too. But it did occur to me there were a couple of things that I took for granted that I don't, basically maybe I shouldn't take for granted. And one of those is this idea of where some of the basic statistical stuff comes from in a real simple little computational PowerPoint thing that we'll spend just a minute with, not too long. And then we'll very quickly get into this standard normal distribution a little bit more. And then we will go over to SPSS and pull up the file from last week that I sent out and look at particular questions and how the analysis for particular questions might work. And in specifically looking at the three different types of t-test: independent t-test, paired t-test, and the one sample test, because those are used, those were actually the first statistics that were developed, but they're also used still today to analyze a lot of data sets. So that's kind of where I'm going with this, and hopefully it'll be, kind of serve a need and get you caught up, and then we can move along a bit more quickly after that. So if that's okay, and if it's too simplistic for some of you, please just kind of hang in there and go drink a cup of coffee or something, and come back when we move on to something that perhaps has a little bit more utility to you. But first, I want to go back over. I want to go over to this PowerPoint thing that I call it just a basic statistical logic, and it's really just kind of the underlying the underlying ways in which the things that we use a lot in statistics, where they come from. And because it is you have to remember these were developed in the 1880s or 90s, pre-computer, pre-calculating machine, all that sort of stuff, done by rooms full of what were called calculators, which were basically younger females in families where the older male had inherited everything. And the younger females were, provided about a third grade education and lived at the behest and mercy of the oldest male in the family, or they went out and found a job. And one of the jobs they could find with their third grade education was to be a calculator in a bank or a factorial house or an actuarial house. Now we call those insurance, but they were the ones at university. They were the ones that did basically all the math, all the calculations, and it was all third grade level math. So the calculation for statistics are inanely straightforward and simple. It's just that when we start layering different pieces on top of other pieces and subroutines on top of other subroutines, they get, kind of a bit more complex, but not really. The basic math is third grade level math. And by the way, when they did invent counting machines, mechanical counting machines, not only did those young females lose their jobs, but they also lost their titles. And so what started out as being called a counting machine by 10 or 15 years later was called a calculator, because it had replaced those rooms full of young British and European females. So yeah, I'm going to go over to the share screen and pop this PowerPoint up. It's up on on the website on As You Learn. It's just called Basic Statistical Logic. And let me see if I can get some stuff out of the way here on my screen so I can actually see it. Okay. Okay. So let me get more of y'all up so I can actually see you. All right. Bingo. It's actually the way I wanted it. And I just refer to this as basic statistical logic because it's just a simple math that goes behind all statistics. And if we have a group of numbers, or some data, some numerical data, and in this data set, I just have 5 numbers. That's all we need. Let's say the mean value is 12, and if you can do the math, add them up, divide by 5, the mean is 12. The deviation scores, which are different from means, they're called the first and simplest measures of what are called dispersion. How is the data set dispersed? And sometimes you could put it on a scattergram, or you could do whatever, but you could also calculate values for how far they were dispersed, and you calculate it from the mean. So 18 is 6 above the mean, 6 is 6 below the mean. And deviation scores, no matter, this one's really symmetrical, but if they're not symmetrical even, deviation scores always sum to 0, which is an interesting, not terribly complex fact, but it makes it difficult to work with that data for any sort of purpose. And so what we do is we square those deviation scores up. Now, keep that in mind, because anytime in math, anytime we square something, eventually we have to unsquare it. And so we square the deviation scores up. And so, a deviation score of 6 becomes 36. And a deviation score of -6 becomes 36. And that adds to, we can add those up to a sum. Well, interestingly enough, that quantity, that sum is called sum of squares. You know, a very logical thing to call it, since that's what it is. But you'll see sum of squares referred to a lot in procedures like ANOVA and different kind of procedures like that, where they use sum of squares as a vehicle to get someplace. And you kind of take into account group size, since there are 5 people in there. You want to know what is the average squared deviation. And this is our first tricky thing that we do in stats, because we have this concept called degrees of freedom. And the notion of degrees of freedom is that when we are selecting a random group, a random set of data from a population, we would expect that random sample of data would look like the population. Well, as it turns out, what that means theoretically is that, let's say we're getting a sample of 20. Well, the first 19 numbers could be anything, but the 20th number is theoretically by random behavior fixed. And so we don't need to get the 20th. We don't need to worry about the 20th number being 20th member being random, because it will be some fixed value theoretically that will make it representative of the overall population. Another way to think about that is if we're flipping coins, and you know, heads, tails, the more flips we get, law of large numbers it's called, the more flips we get, the closer it gets to 50-50, 50-50. But theoretically, it only becomes 50-50 at infinity, an infinite number of flips. Well, if we're one head short and we got one flip left toward infinity, and I know that's an absurdity, but we got one flip left to reach infinity, and when we're one head short, we don't need to make the last flip, because we know it's going to, no matter how we do it, it's going to turn up heads, theoretically, because it always represents a perfect representation of the population it's drawn from. And so we have this notion of what we call n-1 to divide by instead of n, because there's no variance left in the last number in the set. It's a fixed quantity. And I can go into a much longer winded and much more obtuse explanation of that if you want me to, but maybe I'll just try to find a nice little blog piece about why n-1, and it'll probably make more sense than I make. And so anyhow, we don't divide by 5, we divide by 5 minus 1, or 4. And so we get an average squared deviation. Don't forget where this comes from. It's deviation scores squared, and that gives us sum of squares. And then we take sum of squares divided by n-1, and we get what's called average squared deviation, or the more common term, variance. So when we talk about variance within a data set, which we will talk about when we get to ANOVA quite a bit, when we talk about variance in a data set, we're talking about this average squared deviation. Now, remember we had that little issue of having to square things up to get rid of the minuses so the deviations wouldn't sum to 0 and all of that. Well, now we got to get rid of that. And so we take the square root of that, and that gives us what we refer to as a standard deviation. And so all we've done is accounted for the deviation in a data set, manipulated it mathematically, haven't added anything, haven't subtracted anything, until we get this, what's called a standard deviation. And then that becomes the measure by which we can transform raw data into other kinds of data. into standard data. And so when we're talking about standardizing a test or standardizing test scores, that's what we're doing. We're generating this standard deviation so that we then can standardize those test scores. And so we typically standardize scale scores and test scores in terms of units of standard deviation. And so that's kind of how we get there. So definitionally, we know these 5 things. We know what a mean is, just the arithmetic average. Number of cases is n. Sum of squares is that sum of squared deviations for the overall group. Variance is that sum of squares divided by n minus 1, and standard deviation is the square root. And so we've basically gone from squaring that information up to now bringing it back to its original unit. And so if we were talking about pounds, we're still talking about pounds. Or if we were talking about 5 points on a scale of something, we're still talking about 5 points on a scale of something. And so we've gotten back to the original unit, and so we can now talk about those units in a mathematical way. Those were all of the things that were developed in the 1880s, 1890s in these calculator rooms by these young women at the direction of university folks or mathematicians or whatever. Now, we'll talk about standard scores because standard scores are important to the logic of hypothesis testing. And a standard score is simply we take the mean, subtract it from a raw score. In other words, we figure out the deviation for a particular number, and then we divide that deviation by standard deviation, and that gives us what's called a standard score, or as it's more often referred to, a z-score. So the z-score is simply a deviation score for a particular item in a set, a deviation from the mean divided by standard deviation. And that gives us what's called a z-score. Now, and so I've taken the liberty of doing that down here. I did use the right standard deviation, and then yeah. Okay, I've taken the liberty of doing that down here. And so, for example, 18 raw score minus 12 mean gives you 6 divided by standard deviation 5.52 gives you 109. So anytime you see something that talks about standardizing a score, that's exactly what they've done. They've taken a deviation quantity and divided by standard deviation and got, relative in standard deviation units. In that regard, we are now, we can distribute those standard normal scores or z-scores, and we get the basic standard normal distribution, normal distribution. Now, the only difference between this and any other normal distribution is that this is a distribution of standard scores. And if you have all the standard scores in a data set plotted on a distribution, it will look exactly like this in terms of the values that it has at different parts of the curve. And so these units down at the bottom, on the bottom axes, on the x-axis, these are standard deviation units. And so this is 1 standard deviation unit, 2 and 3, minus 1 standard deviation unit, minus 2, minus 3. And the middle is always the population mean, the group mean, the sample mean, or 0 z-scores. Now, the sort of the nomenclature you'll always see for Uh, a group for a population mean is this little mu. And you'll also see this, small sigma for standard deviation. And so they'll always refer to, population mean and standard deviation. I'm going to go to another graphic over here for just a second. Let me stop this share and pop another graphic up here. Where's it at? Did I put that up already? No, I didn't. Let me share that. And this is what I call a normal distribution graphic, just for lack of a better term. And it gives you a little bit tighter look at the percentages of area on a standard normal distribution within different parts, under different parts of this curve. Now, 34.1% of the area under this curve is between the mean and one standard deviation unit up, but also 34% is between the mean and one standard deviation unit down. It's entirely symmetrical. And between 1 and 2 standard deviation units is another about 13.6% of the area. And -1 and -2, same, 13.6. Outside of 2, between 2 and 3 is 2.1% of the area. And below -3 is a little bit less than 0.1%, and that plays all the way out. The curve theoretically never reaches the axis. The curve never gets there. No. If you're interested in geometry of this curve, each one of these standard deviation breaking points is where the arc of the curve changes. So at 1 and -1, what has been a curve on the inside now becomes a concave curve on the outside ever so slightly. And it becomes more concave at 2 standard deviation units and even more concave at 3 standard deviation units. And so there are lots of neat little geometric proofs that you can do for standard normal curve too. But it's a really interesting artifact. And when you put that with the notion of central limit theorem, you realize how big a part normal distribution plays in our understanding of the world around us. Now, every single standard normal distribution, in other words, the distribution of standard scores, will look or have exactly the same areas under the different parts of the curves. So let's say you have a standard deviation, you have a score that's SATs, and you have another thing that's GPAs on a large group of students. If you standardize all those scores, you can compare their relative performance on SATs or GREs to their relative performance on GPA using the same unit, using standard normal distribution units, standard deviation units. So it provides a way of translating back and forth. And, when SAT and GRE do their renorming thing that they do every few years, when the scores kind of creep up, what happens is that they just go in and essentially, take the scale that was existing, figure out the standard distribution notion of that, apply a new mean and a new standard deviation to that, and then renorm the scores. And so voila, 1310 becomes 1298. But it means the same thing in relative terms. Question. Okay. I'm going to go back over to my other graphic for just a second because I want to go another direction with this. Sure, where'd it go? What'd I do with it? Surely I didn't close that out, did I? Okay, give me a second here. I have to go find it. Bump. Bingo, there we are. All right. So essentially the same thing here, 50% is below, 50% is above. So they're at the mean. Standard normal curve, roughly the same calculations as on the other side. But if you round off those surface areas, those areas under the curve, you realize that 68% of all cases or all area is between 1 and -1 standard deviation. And roughly 95% is between 2 and -2. Now, why do we have as a standard the 0.05 level for significance? Because the early social scientists that didn't have a test, when they were looking at individual scores, they would use the test of twos. And so they would say that any student that's more than 2 standard deviation units above the mean is very bright or very gifted. And any student that's more than 2 standard deviation units below the mean is delayed. But either one of those students we would consider to be significantly different from the overall group. And it just so happened that that occurs with about 95% of the area in the middle. And so that's why we have that 0.05 standard in terms of significance level, because that represents or came from this notion of what was called the test of twos. Now, let's now look at and by the way, any little tick mark in between 0 and 1 here, we can know what the area is under the curve at that point. Now, when we look at adding an actual value here, let's say we had a test and it had a mean value of 75 and a standard deviation of 10. Well, at 0 z-score, that would be a 75 would be the 50th percentile, which is a 0 z. At 1, at a standard deviation of 1, we would add 34% more area to that 50% that was out the middle. And so a score of 85, 1 standard deviation unit above the mean, would represent the 84th percentile, roughly. And if we went up to 2 standard deviation units above the mean, a score of 95, that would represent roughly the 97.7 percentile. Now, percentile is different from percentage. Percentage is a ratio of the overall value by some particular counted value. And here we're counting area under a curve. So out of 100% of area under the curve, that would represent 95% of the space. But space under a curve is called a percentile. And so if it's talking about space itself, area or space, then it is called percentiles. It's a little subtle difference, but you sometimes, people will say things and I have to kind of look at it and go, okay, well, you're talking about a percentage as opposed to percentile, and it's a little different. But you can have values for every single tick mark on this distribution. So we know what the percentiles are. Total percentile is for every tick mark. So if we happen to have a z-score value of 1.89, we can know what that percentile is. What does a 1.89 represent in a percentile in that overall distribution? Now, that logic serves as the jumping off point for things like T distributions and F distributions and all that. If we were talking about wanting to know what's a significant difference, it would lie beyond 2 or beyond -2. If we're talking about one direction or another, is this higher or lower? Let's say we want to know if something is significantly higher than the group, then we would bump this back a little bit to which represents 5% of the area under the curve, with the other 95% all the way back the other way. If we wanted to know it was significantly lower, we would bump this back up to 5% on the bottom side and 95% all the way on the other side. Now, wherever those dividing points are, wherever those cut points are that represent that outside significant values, we call those critical values. So for the standard normal curve, the critical values to represent significant differences are 2 and -2. Or if we go down and look at raw scores, 75 and 10, the raw score values to represent the middle 95% of the curve for this test would be 55 at -2 would be the bottom end, and 95 at +2 would be the top end.
Can I ask a question I should know the answer
Sure.
to? Okay. Alpha level, significance level, p-value.
All the same.
That's what I thought, just making sure. Okay,
Yeah,
thank
all
you.
the same. And sometimes it's just called SIG, S-I-G. They don't even bother to call it what it's officially should be. It's officially an alpha level.
Can you say that again?
Yeah, go ahead, Ashley.
There's just a lot of terminology for the same thing, but alpha level, significance level, or SIG, which is what SPSS shoots out in the output, SIG, and p-value are all the same, and then what we use is 0.05.
Yep, that's the standard.
Thank you.
Now, she Ashley mentioned something that I wanted to bring up here in just a second, so I'll go ahead and do it. But are there any other questions on standard normal distribution and significance in standard normal distribution and how it can be used to talk about the raw scores, percentiles, and Z's? And notice percentile uses the same character as percentage, the same representation, although they are technically two slightly different things. Okay.
I'm sorry to interrupt, but Michelle Duran just texted me, and she might be in the waiting room. She got kicked out of class. I just,
okay, I'm sorry.
Did you check? I don't know.
Yeah, let me kill this share and then I can get her back in. I thought I killed that waiting room, but
maybe you did. She's just she's lost in virtual space.
no, she's not in the waiting room. Tell her to go all the way back out and come back in. Yeah, that'd be the best way to do it. Is she on a chat or did I miss her? No, okay, yeah, just going back out, coming back in is the best way to do it. Okay. Okay. Any other questions about this? I mean, this is kind of like central to the whole logic of hypothesis testing. This idea that you can have a curve with critical values on it and use those critical values to figure out whether something's significant or not. Now, it doesn't matter that we don't do the math, but at least you should know kind of what all that represents and where it originates from. Okay. Let me see. Let me go over here. Did I put this up? My goodness, I guess I didn't. So let me pop something else up here that I can get to. Okay. Okay. Michelle actually mentioned the notion of a alpha level, and so I'm going to deal with that terminology right now and have put this up on As You Learn so you can kind of use it as kind of informational. So let me share that up. And bring it up a little bit bigger. Scooch this over so we got a little bit more room there. Okay. In design, we call in research design, we call the two errors that you can make when interpreting a statistic is a false positive and a false negative, and those represent two different kinds of errors. Now, the alpha level error, which we call type 1 error, the alpha level error, is the error that we can make if we say that something is significant and it turns out to be not. So let's say that that we've decided that something is true, and it is true, then we're happy. I mean, we've gotten the right outcome. But if we decide that something is true, in other words, it's met the alpha level, 0.05, it's significant, and in reality, it's not, that's called a false positive, and that's a type 1 error. False positives are type 1 error. If, on the other hand, if we think that an outcome is false, and that is correct, then we're happy. We got the right answer. But if we think that something is false and it turns out that it's not, that it's actually true, that's a type 2 error or a false negative or a beta error. Now, in statistics, we can never know or measure a beta outcome. We can never know a false negative because we have no evidence that anything was going on. We can estimate the incident of false positive, though, and that's that 0.05. That's that 0.05. The p-value, the sig value. But we can, type 2 is the one we just don't know because we don't have any evidence that it's not negative. We can't know that. We have no way of gathering evidence for a beta error. Well, that's not exactly correct. There's some people that say we can estimate beta, but it's rather contrived the way you go about doing it. And it's tied up with figuring out how big a sample size you need, calculating sample size. And so it's I don't know, it's kind of a, I've never found it to be terribly useful, but there are people that will try to do that. But if you follow sort of the traditional guidance, the only thing we can do is estimate type 1 error. We can never know or estimate type 2. We just don't know what it is. Now, what would be there might be a time when we are more worried about type 2 errors. Let's say we had a big bad disease like COVID or like AIDS or like anything else that's going to kill you if we don't do something about it. And if we have a drug that maybe doesn't get to 95% significance level, maybe it's 88 or 90 or whatever, we still might try that drug in a trial because the false negative, the idea of not finding a drug that's useful, is more damaging than the false positive, which is you're going to die anyhow. So occasionally in the medical sciences, when you're dealing with pandemics or when you're dealing with plagues or things like that, yeah, sometimes we do have we do test in a way that might create a type 2 error, but we're really just trying to find anything that might have the possibility of working. And so there are cases in which type 2 errors are the more deadly error, more deadly sin, but we typically think that type 1 is the more deadly sin. To say that something's going to work when it turns out it won't. And that's type 1 error. So alpha error, beta error, type 1, type 2. Questions, comments, overall thoughts? Why in the hell is he doing this? I know, just whatever, questions, thoughts. Oh, yeah, hot chocolate. So if somebody just sees that part of the video, then they'll know that it was hot chocolate.
Michelle said her internet is out, so she'll have to watch the video later.
Okay, that's good. It's always good. It's why I tape, why I record. Because, the one thing we don't have in this country is fantastic infrastructure for broadband. And it's just crappy. Because we have to make a profit off of it. We can't do like the rest of the world and provide it to people for free. Not free, but supported by government. But anyhow, I'm trying not to be political about anything, so I'm being good. So we ready to go play with some statistics a little bit then? All right. First off, I need to talk about the nature of questions. And I need my little thingy patty over here. Geez. Okay. Well, this is not working well, is it? I got too much stuff on this little screen. There we go. Now I can see it all. Okay. So the first question is kind of what we dealt with last week. Is the question, are there differences between two groups? And generally we're talking about, you know, experimental control, or if you have two groups and you're interested in both, they each could be an experimental for the other or control for the other. So we have two groups, and those two groups are categorical in nature. And that's that independent t-test that we did last week and we'll do again today, independent t-test. Now, sometimes there's only one group. And so the question is there a difference between a sample and the population? And if for any reason you can't read what I'm writing, ask me. I'm not, you know, I forgot about cursive in the early stages of my first grade career, and have printed ever since. Okay. And if there is a difference between a sample and a population, that means you've only got one group. You've only got one sample and a population metric, some value that you know about a population. And so that would be what we call the one sample T. And we have, once again, a categorical value for, well, we don't need to talk about categorical value. We have one sample T, and we have continuous variables or continuous data for sample, mean, and population mean. And so remember, sample means are expressed, I mean, if we're talking about them in terms of instead of X values and things like that, samples are generally expressed in terms of Roman letters, and populations are generally expressed in terms of Greek letters. And so a sample mean is an X bar, and a population mean is that mu. And that's just a convention that sample data is Roman numeral or Roman letters and Roman alphabet, and population stuff is Greek alphabet. And so that's two cases. There are three possible cases for t-test. And then the third case is there a difference from pre-test to post-test? And that means we only have one group, but we have two measures on them. We have a pre-test measure and a post-test measure. And that's called a paired t-test. Sometimes referred to as a dependent t-test, but not much anymore. It's almost always now considered to be a paired t. And so you have continuous value, two continuous values on the same group, pre and post, on the same or very similar instrument. And so those are the three kinds of t-test, the three scenarios that t-test will work for. Okay. Well, let's see what that looks like in real data times. Now, I've pulled up, or I'm going to pull up, I've already pulled it up, hopefully I have, into SPSS, the file from last week that we worked with. And let me share that out. If I can find the share button. There it is. It's hiding under there. And so you should see the t-value, I mean the SPSS data file. Now I just for your convenience, I've provided you with the SPSS save file, which is basically the SPSS data file for this, and also for the formative assessment that will be due before class next week. So we can talk about it in class. And so, once again, we need to identify data and what types of data. And so we know that sex or gender is male, female. So there are two groups. We know that part-time, full-time is male, female, is one of two groups. So that could be used as categorical data for an independent t-test. And whether they had remedial work or not is yes, no. So that could be considered categorical for an independent t-test. And so we have two or three independent t-tests there. And then we have multiples of those because we have similar pieces of data for different things. Here's retention from 1 year, from one fall to the next fall. And that's a yes, no too. So we have categorical data, and then we have all these continuous data bits for GPA and credits taken and things like that. And so just for an example, once again, of an independent t-test, categorical, two groups, and a one continuous dependent variable. Let's say that we're gonna do the part-time, full-time thing. And so over here on the first semester, which is that first part-time, full-time status report, part-time, full-time. Where's my little blue thingy? Status, part-time, full-time. We're going to use that for an independent variable. And then we're going to use we'll just use the GPA for first semester to see whether part-time, full-time had any impact on their GPA for first semester. And so in terms of the, let me see if I can slide this thing down. I'm going to have to go out and come back in because I need to pull this thing down a little bit lower. So let me stop the share. Okay, so I'm going to go in and grab the first status. I'm going to analyze, compare means, independent samples t-test, I'm sorry, I got it too far. I missed it. Analyze, compare means, independent t-test. Status, that's the semester one status, part-time, full-time. Oh, excuse me. Not allowed, I know that. That is the grouping variable. And I have to define the groups, and it's, remember, you have to be careful about getting exact syntax here. So it's capital PT, capital FT. Test variable is GPA semester one. I don't need to worry about options. It'll give me the demographic stuff. And so, I'll ignore that. There's nothing else I do here. And so, okay. Now, I have to stop that share and share the output. That's why I like the JASP thing that I used in other classes, because everything's in one set of windows. And so it's not like completely separate windows. It's kind of messy. So we have equal variance is assumed. Equal variance is not assumed. Remember, that has to do with whether we can assume they were pulled from the same population, and that is significant. So since that Levine's test is significant, that means we drop down to the bottom line here where it says equal variance is not assumed. And we look at that data. If this test had not been significant, we would stay on the top line. But since it is significant, we drop to the bottom line. And we see that the t-value is negative 5.593. Doesn't matter the sign, negative or positive, doesn't matter the sign. And the significance level is 0.000. So it is a significant difference between part-time and full-time for their first semester GPA. And when you go up to look at what that was, we see that the full-time folks had a first semester GPA of 3.046 for their mean, and the part-time folks had a GPA of 2.73 for their mean. So the answer to the question, is there a difference between full-time and part-time, is that yes, there is a significant difference between full-time and part-time on first semester GPA. And the difference is that full-timers had an average GPA of 3.06 and part-timers had an average GPA of 2.73.
Can you explain why the Levine, why with the Levine's test being significant, you've dropped down to the not assuming equal variance?
Yeah, okay. Let me see if I can make this screen just a touch bigger. So, all right. Remember that one of the primary assumptions we make because of the logic of the modern scientific method is that the two groups are randomly drawn from the same population. And we know that in most social science settings or most post hoc data settings where we're just looking at data, in the future, kind of post hoc, that we have, whether that assumption or not is valid is something that we really we can't know for sure, but we have to check. And so what the Levine's test does, and it automatically happens in SPSS, what the Levine's test does, it tests to see if those means or variances, remember means are an outgrowth, variances are an outgrowth of means and deviation scores. And so can we look at those two variances and assume that the means must be relatively equal on the two groups beforehand. See, we don't do a test on the front side. So we don't have like a test on the front side to see if, you know, the means are the same. We just have the data and which group they're in. And so the Levine's test estimates what the variance would look like if they came from the same population. And in this case, the Levine said, nope, it's significant. So we know that the variances here, the differences in the variances here is greater than we expect purely by chance. It's in essence, Levine's is like a t-test, except it looks at variance as opposed to, you know, raw values, exact values. And so since it is significant, that means that we can't assume that variances are equal. And so it makes some allowances for that and has a, you know, a couple of things that it works on to corrections that it uses in the formula to calculate that, what in essence looks like a t-test. And so it gets a different t-value. But if you notice, the significance level stays the same or is relatively the same. It's not exactly the same. We just don't calculate beyond 0.000. So probably the equal variance not assumed has a slightly higher significance level or p-value or alpha, but it's 4 or 5 decimal places down the road. So we don't worry about anything beyond 3 decimal places. And so, but we do have to use then this bottom line, which means what we report would be a different t-value, but the significance level would still be 0.000. Does that help, or was that just muddy the waters? But it's one way that the t-test can be examined to see if that assumption of random samples drawn from the same population can be assumed or not. And there's a term for equal variances. There's a term for that. They call it heterogeneity of variance. And it's hard to test means, but it's a little bit easier to test variances for that. And so they test the variances.
So to bottom line it, equal variances assumed means there's not a lot of deviation around the mean in your sample.
Or the deviation around the means are relatively similar between the two samples.
Two groups.
Yeah.
So equal variance is not assumed means there's just more difference between the two groups than expected.
The deviations are different between the two groups.
Okay.
And it's another reason why there's, you know, we always have to be careful about how definitive a statement we make when we're dealing with statistical significance, because we're assuming equal variances. We're assuming random selection. And, you know, we very seldom have that. In fact, we never have that in post hoc data. But, you know, at least the t-test allows us to check that, or Levine's test. So anyhow, yes, there is a significant difference between the two groups, and it's in the direction of the full-timers having higher GPAs. Okay, well, let's ask another question. Different question. I think my, you know, ALEXAO-A over there, I thought I was mentioning her name. So anyhow, she's not sure, so that's okay. Now let's ask a, it's kind of that one sample question. Let's say that we know that overall GPA at this community college is 3.05. That we know that the overall GPA across the entire college is 3.05. And we ask the question, is the GPA of this group of students in this study different from the overall GPA of the college at 3.05? And so we have one group, which is the group we're studying, and we have a population value parameter. When it's the population, we also call them parameters. We have a population parameter of a mu, population mean, of 3.05. And so we can go in, and once again, we're going to analyze, compare means, except this time we're looking at a one sample t-test. And we're looking at a first semester GPA for our group here of whatever it is. And the test value, there's a box down here for test value. And the test value, we enter that value, 3.05. And so the population value is 3.05. And we want to know whether this first semester GPA is different from that. And there are no real options that we can play with here or do anything with. And so we just, okay, now let me stop share and start share again.
Is that 3.05 is your mu?
That's the mu.
Okay.
And we always have to know a population parameter for a one sample test. You know, you have to know that value. Like, you know, if you wanted to know whether a test group in a medical study was, you know, normal height for the country, you'd look at a population height value that's estimated by the U.S. Department of Health and Human Services. And so you always have to find or know, or let's say a particular school's ACT, average ACT score or average SAT score, is that different from the state average? Then you have to know what the state average is. And so you have to find that. But once again, this is a one sample test. The mean for the sample was 2.81 compared to the test value of 3.05. That is significant. And we don't need to worry about sampling or assumptions of variance because we only have one sample. So we don't need to know whether it's equal or different from another sample or not. And so the significance level is 0.000. And so the answer to the question is that this group GPA, this test group's GPA, is significantly lower than the overall college average. 2.81 is significantly lower than the overall college average of 3.05. Now, we're not going to talk about Cohen's today, effect size, but we will come back to that. But in terms of how big an effect this would be because of this value here, this point estimate, it'd be a fairly small effect size. So this is not a big deal. It is significantly different, but it's not like it's so different that we're going to throw up our hands and run to the hill screaming different. It's just, there is a difference, a significant difference, but it's not a biggie. And, the value we would be thinking that it was, something to worry about would be a 0.50 or negative 0.50. Something that we would run to the hill screaming would be a negative 0.80. And so those are just values that, having done it a while, what values to look for. But I will give you a reading on Cohen's D, so you can understand what that means. But let's say this is a significant difference, but it's probably not a big one, not a huge difference. But it is significant. It's outside of that 95% middle range. Okay. All right, let's add the third question now. And get rid of this share. Let's say our third question is, there a difference from pre-test one, GPA first semester to cumulative GPA? In other words, is the first semester representative of their overall GPA at the end of 2 years? So I want to know, is their GPA first semester representative of their GPA cumulative after 2 years? Now, one thing I know is that the end's going to be a little smaller because you will have some attrition. You wouldn't have a transition from year to year of 100%. And I'm also going to, know that, there's probably going to be some difference in the other characteristics of these students that hang in there for 2 years versus ones that don't hang in there for 2 years. So, we know that's, there will be it'll be a different clientele, but it will only be those subjects that were there first semester and are still there 2 years later to have a cumulative GPA. And since we got one group of people and two measures basically calculated the same way, two standardized measures that are continuous, I can do a pre-test, post-test, or a paired comparison test. So let me go back over here and pop up that share. So here I have GPA first semester, and then way over here, well, not way over there, but over there, I have cumulative GPA. I guess the last one would be the third semester. Cumulative GPA third semester. And so I go into analyze, compare means, paired samples t-test, paired samples t-test. I need to give it the 2 bits of information. Oh, crap. I think this is GPA semester 1. We'll see. Yes. And cumulative GPA, where's my cumulative GPA? I guess GPA semester 3 will be what I have to use. And so I've got, yeah, there is cumulative GPA semester 3. So I've got the 2, see, I couldn't see all that because of the screen over here. And there are no real options for it. Once again, there's nothing I can really tinker with to give different things. I can standardize those in different ways, but I'm just going to use a standard deviation of the difference, which basically takes the standard deviation for semester 1 GPA and the standard deviation for cumulative GPA and splits the difference in terms of what they use on the bottom of the equation to get the t-test. And okay. And now I need to stop the share. Don't you really like the way I have to talk my way through this before I screw it up? Sometime in your future, you will have to talk yourself through these things too. Trust me. And it will save you some time. So there's the paired sample statistic for the t-test. cumulative GPA semester 1, 2.81, cumulative GPA semester 3, 2.80. Guess what? They say there is a significant difference there. I would suspect that the effect size of that, no, that's correlation, I'm sorry. The t-test is down here, mean standard deviation, the significance level is over here. So 0.617, so there is no significant difference between their first semester GPA and their cumulative GPA after 3 semesters. And so the answer to that question is no. And so those are the three t-tests. The let me turn that share off and come back over here. How did I end up without my video? I don't know. Hey, I'm back. I guess I clicked something down there earlier. I'm sorry. I know you need to see my smiling face as we go along, so you know, I'll throw that back in there. What? Yeah, some people like my face. Yeah, mostly family members, close family members, but some people. Questions about t-test? That's all we can answer with t-test. Now, the obvious next question is, what if you have more than 2 groups? That creates a little bit of a difficulty for us because we don't have an answer for that. We don't know what to do with more than 2 groups. And we're going to quit at 5, so don't worry. We're not going to go much longer. We really don't know what to do with 2 groups, more than 2 groups. We could run multiple t-tests. Okay, we could run multiple t-tests of all, say for example, we had 3 groups. That means we're going to have to do 3 times 2 divided by 2. We're going to have to do 3 t-tests to get all the possible tests between the 3 groups. AB, AC, BC, if we label groups A, B, C. If each one of those tests has an alpha level of 0.05, and we have to run 3 tests to answer our question of differences between groups, then we're not really testing 0.05, we're testing 0.15, because we're doing 3 tests that have a 5% alpha error level in each of them. And so we have actually a 15% possibility of getting a false positive. And so once you get beyond 2 groups, t-tests are kind of not useful, and they won't work, but except with 2 groups at most, or 2 pieces of data at most. And so we had to come up with a way of doing that. I'm talking about the statistical folks historically in general, had to come up with a way of dealing with more than 2 groups. And so they developed what's called analysis of variance, which allows us to look at as many groups as we want to all at once under 1.05. And after that, after looking at the overall analysis under 1.05 and finding that there's a significant differences between some groups, then we have to go in and explore using what are called post hoc tests, essentially sort of like t-test, but not quite. Post hoc tests to see which particular groups are different from each other, because it might not be all of them, probably isn't. If we have 4 groups, maybe it's only a difference between groups 3 and 4 or 1 and 3 or whatever. And so we can know if there is differences between groups under one umbrella test, which lets us stay under that 0.05 alpha level, but then we have to dig deeper using what's called a post hoc test to actually find what's going on. And that's what we will play with I'm going to put up a video that I used in the stats class in which I, kind of went through an explanation of ANOVA. And I'll put that up so you can kind of look at that beforehand. You have that little formative assessment piece. Maybe we need to go look at that very briefly. Let me see if I can get over to the web page. Well, I'm gonna have to get rid of some stuff here. Just a second. Excuse me. I've got too many windows open. Okay. Now we're back over there. Now I'm gonna share up the okay. So over here in your as you learn, you'll find the arrow types, you'll find that little basic stat logic thing, you'll find the normal distribution graphic, you'll find this formative assessment, a CSV file, and formative assessment SPSS file. And you'll also find this formative assessment, which, oh shoot. Let me see if I can get this to come up without having to switch over. Nope. All right. Sorry. I'm going to have to switch over to Microsoft Word. So, oh, wait a minute. Stop sharing, share screen. Sure. Okay. So you'll see to load the file and answer some very simple questions. Just more of a, repetition thing just to get you to think of things correctly. And you've got some pre-test and post-test and change scores, from one test to another. And then you've got a couple of categorical variables, group number and gender. And what are the means and standard deviations for each of the two pre-test measures? What are the means and standard deviations for each of the three post-test measures? What are the minimum and maximum change one scores that would define the middle 95th percentile? Remember, that's the -2 standard deviations below the mean value plus two standard deviations above. So that's just a matter of, doing a little calculation there, just to running descriptives and all that. And is there a significant difference between genders on the final post 3 score, independent t-test? Is there a significant difference between genders on the pre-1 score, t-test, independent t-test? Is there a significant change from pre-1 to post-2, paired t-test? And if the national average post-3 measure is 49.5, are the subjects in this experiment significantly different from the national average, one sample t-test? So it's just a little practice and running those things on a new data set. And remember, you just need to get this done before class. You don't have to submit it. I'm going to do a video that kind of walks through the answers to that, put it up the day we come to class, or either build a video the day of class as we kind of go through that, and answer questions that you might have as to how you got something different or not. And that's the first formative piece. And then from there, we'll add ANOVA and correlation and regression, multiple regression or regression. And then the next formative assessment will include a couple of questions on t-test and things like that, and questions on ANOVA, and questions on correlation, and questions on regression. And then, we'll add the next piece, and we'll kind of do it that way so that you have a chance. Now, we're going to start relating these to the articles also next week. So if you look at that first article I gave you, notice that it uses t-test. And so we need to talk about how the question evolved, what type of question was it, what we can draw, and what sort of inference we drew from answering that question, and how we talked about that in the write-up. And so we'll do, kind of that whole thing, so you can see how you go from the question to the data to actually putting that in something. And then I'll try to pull up an article that's got more ANOVA in it and more correlation and regression in it, and we'll just kind of go from there. And that's the way we'll walk through. Now, we need to talk about project, and I will send you a more detailed rubric for the outcome project, which is basically a little perspective of how you might use a quantitative approach to analyze a little bit of data under that umbrella, what kind of measures you would use, and maybe what kind of data analysis you would use, and things like that. So, questions, comments, gripes, personal remarks about my new haircut I just got today. I only took off 3 inches, so my wife likes it. That's better. So, no questions, no comments, no thoughts. All right, ladies, 5 o'clock, hour and a half being, we're out of here. I'll put the video up. I'll get the other stuff up that you need, certainly tomorrow, probably. I don't think it'll be later than tomorrow. And so the video about ANOVA and things like that, and following through with the correlation and all that. So I figure I've made those for another stats class. I might as well use them in here too. All right. Well, y'all have a good evening, and have a good weekend. Enjoy your day the next day or so, because I think it's supposed to rain all weekend. And, stay safe. Yeah, stay away from all those bad people and all the bad things that are running around out there, and let's all get through this thing. Okay. So have a good week, have a good evening, and I will see y'all next week.